Good morning. So, last chapter for CCNA 3. So, OSPF tuning and troubleshooting. So, we're going to look at advanced configuration for single area OSPF. Of course, these will apply to multi-area OSPF as well. No great difference there. And so, we're going to look at configuring a way to influence the DR/BDR election on multi-access networks, so that they'll so you can actually choose which routers will typically be DR and BDR. We'll also look at propagating a default route, and we'll also look at interface settings like the hello and hold times for the to tune the network performance, basically. Then troubleshooting, we'll look at the processes and tools that are involved in troubleshooting OSPF, and we'll look at finding missing route entries on OSPF version 2 and 3 routing tables to try and fix some problems that can occur. So, of course, I have mentioned it previously that OSPF basically classifies different types of networks, and so the ones that we're going to talk about today are the ones that have multi-access in the name. And so point-to-point, of course, is not. There's only 2 hosts on that network, and so it's very easy. There's no need for DRs and BDRs because there's only 2 routers. There's not an overabundance of communication possible. On broadcast multi-access networks, of course, like an Ethernet network, there is the possibility for lots of routers, and so that's when lots of adjacencies can mean lots of the link state updates, and so it can from there take up a lot of bandwidth for not necessarily the most efficient use of that bandwidth. So non-broadcast multi-access networks are actually for wide area networks, and so frame relay is the most common one for that. And so you can actually set up a it can be very much like an Ethernet network on a WAN, and so you can have lots of adjacencies again. So springs here. And so again, having a DR/BDR will sort of make the traffic more efficient. Point to multi-point again. So that's another type of network. And then virtual links are actually sort of the links that are used by Cisco to sort of break the rules about all areas must directly connect into area 0. So we won't have to worry about too much about that. And so, as I said, multi-access areas create 2 challenges regarding the flooding of OSPF link state advertisements. And so, sorry, I was expecting more text from that. And so basically, the more routers you have, the more adjacencies you get, and so it grows exponentially. And so from that, that means there's a lot more packets going around when there are topology changes in the network. And so to fix that problem, on multi-access networks, we have a DR/BDR election. So designated router, backup designated router. And so the DR is basically the central communication point for that network. So you'll notice in the diagram here that there is an Ethernet switch in the middle, and all of the routers are connecting into that. And so, so basically each router could have 3 adjacencies. For 4 routers, there'd actually be 12 adjacencies running just on that network. And so every time there's a topology change, there'll be at least 12 LSAs getting about. And so it starts getting very busy. And so if you elect a DR, basically whenever there's a topology change, the routers will tell the DR, and then the DR will tell the other routers. And so it basically gets down to one-to-one communication. There's no wasted packets sent. And so, of course, the BDR is there in case the DR fails, and so it will take over in that case. All other non-DR or BDR routers are called DR other, or sometimes drother, but anyway. And so when it comes to adjacencies with those routers, they will have full adjacencies to the DR and BDR. They will have only two-way adjacency to all other routers, which means they've just seen hello packets from one another within the last dead time. Instead of flooding LSAs to all routers in the network, DR others send their LSAs to the DR and BDR, and they use a multicast address of 224.0.0.6. And so that's a multicast address set aside for OSPF that all designated routers will listen on. So OSPF will automatically elect a DR and BDR on a multi-access network, and so you can of course look up the settings to see what has happened. And so according to this diagram here, R3 is the DR, R2 is the BDR, and R1 is the DR other. And so there are several ways that this election occurs, and so we will go into more depth in the coming slides. And so if you do show IP OSPF neighbour, which is what I normally do to look at both adjacencies and who is the DR BDR, you can see that router 1 tells us that router 2 is the BDR and router 3 is the DR. Now, of course, because router 2 and 3 are either the DR or BDR, you only see the other and the DR other, basically. And so now we don't have two DR others in this, and so we don't have any two-way adjacencies. But anyway. When I do my demo a bit later, I've actually got 4 routers, and so there will be two-way adjacency. And so how do we decide on who's going to be DR and BDR? And so the first thing that is checked is the interface priority for that interface that's on that multi-access network. And so basically it's an 8-bit number, and so you can have a value from 0 through to 255. The higher the number, the better chance that the router will become DR. By default, they're set to 1, so that's not very high at all. If you set the priority to 0, that router will never become DR or BDR. But of course, higher than 1 will increase its chance of becoming that router. So of course, because the default is 1, if no one has configured it, we still need to have a way to figure out who the DR and BDR is, and so there's a tiebreaker. And then from there, it's actually the router ID that is used. And so, and if we looked at the previous slides, you'll notice that the router ID for router 3 is 4 3s. The router ID for router 2 is 4 2s, and the router ID for router 1 is 4 1s. And so that router ID was what was used to determine that. So router 3 had the highest ID number, and so it became the DR. Router 2 had the second highest, and so it was BDR. Now, of course, how do we get the router ID? And so again, if you've done the router ID command, that's the preferred method. If that hasn't been done, the router will look for any loopback IPv4 addresses. If there is one, the highest one, or at least one, the highest address will be chosen for that. If that is not true, there's no loopbacks, it will then use the highest IP address on a physical interface. And that is the non-preferred method because, of course, physical interfaces can go down and make things unstable. Now, the DR-BDR election doesn't happen very often. It only happens when the processes start up again or the DR fails, basically. And so if you configure a router that's already adjacent to other routers and there's already DRs and BDRs elected, if you raise its priority, it will not change that to be the DR until there's some reason for a new election to happen. And even then, it may not become DR or BDR, depends on what's going on the network at the time. Now, how do we do that? So it's the command on an interface basis is IP OSPF priority, and then you put the number in. So, of course, the default value is 1. You can put a 0 if you want that router not to be DR or BDR, and of course a higher number if you wish it to be more likely to become DR or BDR. And so, of course, for IPv6, it's exactly the same command except it's IPv6. So changing the priority of an interface from 1 to a higher value would enable that router to become DR or BDR during the next election. It doesn't happen straight away. And so to force an election, you can either shut down the interfaces and restart them again, or you can do clear IP OSPF process, and that will do that as well. And so that just basically clears all the settings, and so it has to re-establish adjacencies, and so it will then cause a new election often. Now, default route propagation. So if you remember RIP from CCNA2, it's basically the same process as that. And so, of course, you put in your default route, which is your IP route, quad 0, and then a next hop or an exit interface. And then you just put in the command default information originate. And so this router, in this case router 2, has the default route, and it will advertise that route to the other routers. So very much the same as RIP, but of course different to EIGRP that we did a few weeks ago. And so, of course, show IP route. With IPv4, you get that gateway of last resort line. And so, of course, as long as it says something other than is not set, we have a default route. And then, of course, we can also look inside the routing table as well. And that S star means the star means it's a candidate to be the default route. It's the only S star there, so it will be the default route. So IPv6, exactly the same, of course, other than creating the default routes a little different, because you've got to use IPv6 addresses. And so, of course, there's your default route, and there's your next hop in this instance. And again, default information originate, and away you roll. And so, again, showing the IPv6 routing table, you've got this S route. They don't have the gateway of last resort line in IPv6 routing tables, so you've just got to look for the route to that. Now, another tuning thing we can do is the hello and dead intervals, and so this is what it was talking about with the efficiency of the network bandwidth. And so if we're talking about hello and dead intervals, by default they're 10 seconds and 40 seconds, so 10 seconds between each hello packet, 40 seconds without receiving a hello packet from that neighbour is when you declare it gone and start recalculating your routes. And so when you do show IP OSPF neighbour, it actually displays the dead time that's left until it will be declared dead. As long as it's over 30, things are working hunky-dory, I suppose, because it's happened in the last 30 seconds. I mean, you know, so, sorry, within the last 10 seconds there's been a hello packet, sorry. Now, of course, you may want to change that, and so you might want to shorten the times so that there's a quicker response to a router going down. That's certainly possible. Or another one might be that maybe the link is a little bit busy and you might want to decrease the traffic over the link, and so you can make the dead time larger. So, of course, you've got to consider, you know, you normally do at least 3 or 4 times the amount, the dead time longer than the hello interval. You know, you got to be able to account for at least 1 or 2 missed packets beforehand. So again, if you drop the hello interval down to 5 seconds, you might set the dead time to 20 seconds. So that might be what you want. Halve it all. Of course, you might want to increase the time as well. If you do no IP OSPF hello interval or dead interval, of course, that will reset things back to default. Now, remember that the hello and dead intervals are sent in hello packets, and both routers must have the same setting for them to form an adjacency. So if you change one router, you've got to do the other end, otherwise it will die and it will not exchange routes. So got to be careful with that. And so setting it for OSPF version 3 is exactly the same, except of course you put IPv6 in the command. So no great differences there. So how do we troubleshoot? And so often the problem is that OSPF adjacencies will not form. And so why would that be? And so the reasons I've given us is the interfaces are not on the same network. And so basically that's sort of a hard piece of language to sort of handle. It really means is they're connected into the same Ethernet network, but their addressing isn't part of the same network. And so someone somewhere has addressed at least one interface incorrectly. And so that's why, that's what it means by that. So the network types do not match. And so if one router thinks it's a broadcast multi-access network and the other end thinks it's a point-to-point, they will not form an adjacency. That doesn't happen very often. Hello and dead timers do not match. And so, again, you've got to make sure that they're coordinated amongst all the routers. Interface to neighbour is incorrectly configured as passive. Well, passive interface has its advantages, but forming adjacencies is not one of them. If you've fouled up with your network commands, so you've missed one or typed it incorrectly. Authentication is another thing that you can misconfigure at times. And of course, the actual interfaces must have an address and, of course, must be up for them to be able to exchange packets to actually form an adjacency. So, as we said, the adjacency state will go from down all the way through to full status if things are working well. Another happy result is a two-way state. If that host is a DR other and with other DR other hosts, that's all they need to have, which just means they've seen hello packets from one another. And so, of course, basically you've got the init state, which means things are starting up, which really means one of the routers has sent a hello packet and the other one hasn't replied yet. Two-way, of course, means both have done it. And so exchange start means they've started exchanging routes. And then exchange state is they've done some more of that. And then loading state is where they're actually starting to calculate routes. And so, as I said, the two states you want to see are either two-way or full state. Of course, I suppose full state gets more done for you. So how do we figure these things out? Show IP protocols. For IPv4, it tells you a fair bit of information. Show IP OSPF neighbour, again, that tells you the status of them all. Show IP OSPF interface will show you information as well. Show IP OSPF. Show IP route OSPF shows you what routes you've learnt. And of course, clearing the OSPF process will, of course, reset things. Now, the most common problems with OSPF can either be neighbour adjacencies not forming, missing routes, or poor path selection. So, of course, to troubleshoot that, is the neighbour table correct? And so you think it should have X number of neighbours. If it has that, all good. If it doesn't, that's when you might start looking into that. So show IP OSPF neighbour. You also might want to debug IP OSPF events, I think it is. And that will actually show you when hello packets arrive, and will actually also display the information of if it's not forming an adjacency, why. It might say, you know, interval timers are wrong, or whatever it might be. Now, if the adjacencies are all correct, then does the routing table look correct? And so, of course, show IP route will show you that. And so you can look into it. You know, is that going through the correct links to the correct networks and so on? And then from there, so do we have the right routes in the table, and are they being forwarded in the right direction, basically? And so with that, you might actually consider things like, is the cost correct on those links? So you might need to do bandwidth commands or IP OSPF cost commands and things like that. So they're all things you might want to consider. So with the neighbour issues, show IP route, of course, will tell you if you're learning routes. Show IP interface brief, show IP OSPF interface, and so on. And of course, looking for passive interfaces is another thing you might want to do. Serial 000 is probably not a passive interface you want. And so you might want to reverse that. And so apparently this route isn't appearing in the table, and so they'd forgotten to put in a network command. And so, of course, that will certainly help things, correcting your network commands. Now, troubleshooting IPv6 or OSPF version 3, not greatly different at all. The process is exactly the same, pretty much. Of course, you just got to remember to put IPv6 in the commands. That's about it. It works in the same way. I've got to admit, in my opinion, the information on show IPv6 protocols is not as useful. It's a lot more brief and just not as interesting, I don't think. But anyway, but show IP OSPF neighbour is certainly a worthwhile endeavour. And so in this example, router 1 is not receiving the R3 LAN OSPF v3 route to Cafe 3, basically. So verifying router 3 routing protocol settings reveals that it's not enabled on that interface. And so basically they need to, of course, because it's IPv6, it's not a network command, it's that interface command that relates that interface to that instance of OSPF. And so now it should be advertised, and away you're off. Now, multi-area OSPF skills are not greatly different to single-area OSPF. I suppose it does add a little bit of extra complexity in that you might wish to summarize routes, but apart from that, not greatly different really. The adjacencies work the same. So the routing table might look a little different because you'll might have inter-area routes appearing as opposed to just normal OSPF routes, but not greatly different. So, of course, with multi-area OSPF, those routers on the boundaries can well have more than one database, those area border routers. And so you've got to consider that. Okay, so the chapter summary. And so we spoke about the 5 types of networks. And those ones with multi-access in the name are basically the ones that need the DR, BDR elections. And so on those multi-access networks, the reason we need DR and BDRs is to stop lots of LSA flooding. I'm going to say some flooding will happen always because that's the way OSPF works, but we don't want it to be excessive. And so having a DR and BDR means that it's a lot more efficient when it comes to traffic for OSPF. So everyone tells their troubles to the DR, and then the DR will then advertise that to everyone else. So the election process for DR and BDR, of course, is the first item is interface priority. Of course, the default interface priority is 1, and so if no one's configured things, it needs a tiebreaker, and that will be the router with the highest router ID. But leaving it at router ID, it's a bit of a blunt tool. It's not particularly precise. Having interface priorities is a lot more precise. You can actually specify which router it is by that priority, and you can actually, if you've got more than one multi-access network, you can actually have one router being DR for one area and another router completely, instead of it all falling on that router with the highest router ID. So you can manipulate these elections to work in your favour and share the load. So of course, propagating default information is much the same as RIP. And so default information originate once you've got a default route in, and it will look in the table similar, at least for IPv4. It'll be an external route if it's learnt through OSPF to the other routers. Of course, you can play around with the hello and dead intervals. Just be careful. Another thing we didn't talk about in the slides was, it did get mentioned, I think last week or the week before, was the auto cost reference bandwidth. And so if you remember, OSPF was written back when 100 megabits was as fast as network you could find. It's changed now. And so you can basically define a higher reference bandwidth so that it will modify the bandwidth calculations, cost calculations, and then you'll have a more meaningful metric for those faster routes, instead of the normal having the cost of 1. And so troubleshooting, show IP protocols, show IP OSPF neighbor, show IP route, they're my top 3. The other ones can be show IP OSPF interface, show IP OSPF. And of course you can clear things if you might have changed things and they haven't resettled yet. Troubleshooting between version 3 and version 2 is very similar. You've just got to remember to do IPv6. So there's the logo. Okay, I'm just going to stop the recording for now. I was about to say, like,
Yeah, I've been